experiment illustrates how an object fired horizontally from a high mountain under the influence of gravity can follow a curved path, eventually either falling back to Earth or entering orbit. The speed at which the cannonball is fired determines its trajectory. Slower speeds result in a shorter distance traveled before falling, while faster speeds can lead to an orbit around the Earth.
To fully express and prove his theories, particularly concerning motion and gravity, the existing mathematical framework was insufficient. This necessity drove Newton to independently develop calculus. The creation of this powerful mathematical tool was a monumental intellectual achievement in itself, but it was also a complication as he had to invent it alongside formulating his physical laws.
To understand the natural state of objects, Newton was driven to understand what happens to an object when it's not being acted upon by any net force. He questioned whether the natural state was rest, as Aristotle suggested, or if there was another possibility. His thought experiments led him to a revolutionary idea that uniform motion, or constant velocity in a straight line, is as natural a state as rest. The prevailing Aristotelian view of motion was complex and in Newton's view didn't accurately reflect how the world truly worked. Aristotle believed that a continuous force was necessary to keep an object moving. Newton sought a more elegant and consistent framework that could explain both terrestrial and celestial motion with a unified set of principles. The benefits of discovery enabled more accurate predictions. By understanding inertia, scientists and engineers could make more accurate predictions about the motion of objects. This was crucial for fields like ballistics, astronomy, and the early development of machines. In essence, the discovery and formalization of inertia by Newton was a pivotal moment in the history of science. It provided a fundamental principle for understanding motion, laid the groundwork for classical mechanics, unified our understanding of terrestrial and celestial realms, offered simpler explanations for everyday events, and spurred further scientific progress. Its impact continues to be felt in virtually every branch of physics and engineering.
Uses a coin, a glass of water, and a note card. The procedure steps are to get a glass of water and place a note card on top of the glass. Place the coin in the center of the note card, then flick the card horizontally. The coin will then fall into the glass because the coin will remain at rest due to inertia.
Newton's first law of motion, or the law of inertia, has led to significant advancements in various fields such as automotive engineering, space exploration, robotics, and sports sciences.
Today, Newton's first law is beneficial in modern times to a wide range of people. Here are some examples: space engineers, civil engineers, educators, automotive engineers, architects, astronauts, and even other students. Newton's first law is making advancements in various fields such as medical science. Inertia is considered in the design of medical devices such as prosthetics and implants to ensure they function within the human body. It's also helpful in environmental engineering. Newton's first law helps in modeling the movement of pollutants in air and water. Understanding how these substances will continue to move unless acted upon by external forces, engineers can develop better strategies for pollution control and environmental protection. Material science is another field. Newton's first law is used to study the behavior of materials under various forces. This is helpful in developing new materials with desired properties such as strength and flexibility. And lastly, for an example of a field, is biomechanics. Inertia is used to analyze human movement and develop better athletic training programs, ergonomic tools, and rehabilitation techniques.
The question we chose to ask how much tension would be on a rope pulling a 25 kilogram object up at 2 meters per second. This question shows that the forces on an object must be able to resist to successfully hold the weight and move the object up. With gravity being a constant force acting on objects on Earth, anything being suspended in the air by a rope or other object will have to resist the force of gravity to hold the object, thus creating tension. The pulling force exerted by a stretched rope or cord on an object to which it's attached is called a tension force.
The benefits to understanding this question can help in multiple places. First, it can help manufacturers to design their ropes properly to withstand the repeated forces of lifting heavy objects on holding them at length. Another benefit of understanding the forces applied by this way is for the workers and their safety. Having knowledge of the rope's limits and the force applied can help prevent accidents and injuries due to overloading the rope and breaking it.
To come up with this question, I used my personal experiences of my job to help think of something a bit unique. I have witnessed multiple incidents occur due to ropes breaking under heavy forces and unfortunately witnessed injuries as well. The question is not very difficult to solve and can have a good chance of stopping a problem from occurring by understanding the things you are working with. I had considered other questions on relation to force, like how much force to move or stop an object, but these questions are so common I wanted to try and relate something more personal to the subject. Most questions I see for Newton's first law will relate to forces required to move or stop an object. An example of such a question is how much force must be applied to stop objects with a mass of 10 kilograms moving at 20 meters per second. I found the question to be more unique due to it posing a question on a resistance to gravity while suspended as opposed to resistance of some other outside force. The question puts into perspective the tension force applied to a suspended object.
Few factors to consider: mass, acceleration, and velocity. Due to the given mass and a constant velocity, acceleration will be zero. Whenever force is applied to an object, it will accelerate based upon the force applied and the mass. This will also cause a corresponding amount of tension to be applied to the rope.
Tension will be equal to the weight of the object. Therefore, we need to calculate for the weight using our given kilograms and gravity. We would also need to account for acceleration. Due to a constant velocity, however, the acceleration will be zero. We also must keep in mind the gravity constant throughout the problem, which is 9.8 meters per second squared. Lastly, newtons will be the desired unit for tension. 1 newton can also be expressed as 1 kilogram meter per second squared.
The first thing we can do is determine the weight of the object. To do so, we will calculate 25 kilograms times 9.8 meters per second squared, or the force of gravity. This will give us 245 kilogram meters per second squared, or 245 newtons. As mentioned previously, we would need to account for acceleration of an object being lifted to find the tension. However, due to the object moving at a constant velocity, the acceleration will actually be zero. Due to acceleration being zero, our tension will be the 245 newtons. To verify the calculations done, I double-checked my work and process against some other texts available online, as well as calculating on 2 different calculators to ensure that I had done the process correctly. After I had repeated it multiple times, I came out to the same answer, and I'm confident that we got this one right.
In addition to Newton's first law, Isaac Newton also made other contributions to physics, including Newton's second law of motion, which describes how force affects the acceleration of an object, and Newton's third law of motion, which means that for every action there is an equal and opposite reaction. Isaac Newton also studied with scientists including Aristotle, Copernicus, René Descartes, and Galileo. Isaac Newton developed his first law of motion in 1666 when he was 23 years old. He presented these laws in his seminal Principia Mathematica in 1687.
As a group, we learned that there are a lot of jobs that use Newton's first law of motion in some kind of way, which was honestly unexpected but interesting to learn about. One thing we would like to learn about more would be the other laws of motion that Newton discovered to get more information on those as well. One topic we think would be interesting to work on would be the laws of thermodynamics.
Newton's first law states that every object will remain at rest or in a uniform motion in a straight line unless changed by an external force. The project went pretty smoothly, gathering information and working together. The part that we feel was most important working on the project was how Newton's first law is used today in many different fields and is still continuing to be used invaluable.